this is the first of a sequence of 3 lectures on an introduction to machine learning. The 3 lectures will focus mostly on the conceptual underpinnings of machine learning and are agnostic of the application in which they are utilized. However, we do have 2 lectures, the first of which is going to be given this afternoon by Enrico Camporeale on applications of some of these concepts and some of the concepts we will be covering in the coming days in heliophysics. So what I'll be talking about today mostly is really an introductory description with the idea of building up to the deep nets, which are the essential building blocks of a lot of what you see both in supervised and unsupervised machine learning. And so the development is the following. Ultimately, I want to get to this concept, the most prevalent building block in a lot of machine learning applications. But the way I will build that up is to talk about some familiar things we have already seen in regression and the generalization of that to logistic regression. And again, generalizing that further to support vector machines, which are all tools for classification. I'll start by talking about binary classification and then generalize that to multi-class classification. And then generalize that to essentially the final goal, which is using deep nets as universal function approximation. So when you have many classes, you can describe a function as a combination of those classes and represent a function in a generalization where you have essentially asymptotically many classes that defines a function in a high-dimensional space. I've included a reference. There are hundreds. This one focuses more on a probabilistic view. Of course, the history of what today we recognize as a prevalent development in AI everywhere in our lives has influences that have come from many directions. I've just listed a few from 1930s to 1950s in the context of neurology research that showed brain as an electrical network of neurons. Of course, the work of Norbert Wiener on cybernetics, which described control theory and stability in electrical networks, information theory, as developed by Claude Shannon, in the context of theory of communication, and theory of computation by Alan Turing, describing the digital nature of computation, and electronic brain and neural net, the terminology by Walter Pitts and Warren McClough. And there are many others, of course. But I want to show you an interesting abstract to a proposal that was submitted in 1955 by Marvin Minsky. And in particular, this was for a summer school in Dartmouth on artificial intelligence. This is the beginning of the first wave of artificial intelligence development. And in particular, I want to draw your attention to some of the wording. So it says, this study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. And it had elements of how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans and improve themselves. So all of these, automation, for example, self-autonomy. Okay, so what were some of the elements that appeared and discussed? Automatic computers, programming as a computer with language, called neuron nets, theory on complexity of calculation, self-improvement, abstractions, randomness, and creativity, all of these topics, as early as that time. Of course, in more recent years, we have seen ubiquitously that some of these concepts have made their ways into elements surrounding us. As an example, I've listed some here. remember Deep Blue and IBM, where for the first time around 1996, there was a game with Kasparov where for the first time a machine beat a chess master at the international level. That competition repeated just to make sure that it wasn't a fluke. A year later in 97, same thing happened. So it was a transition in terms of machines that can have that level of sophistication in a game as complex as chess. We all remember Watson from Jeopardy. That was an interesting development where it could actually play, and in some ways, of course, there were some hints, if you remember, of awkwardness or hallucinations that sometimes would come up in terms of answers to Jeopardy questions. But nevertheless, it really performed impressively. Games have been very important because of the difficulty, both in terms of interactions with humans, but also computational challenges. And so they have been central in the development of many of the both hardware and algorithmic advances. Game of Go, again, 2016. We don't need to say much about autonomous driving. We know where it is. We know how it's been evolving. And of course, this is perhaps what most familiar the public have been exposed to and influenced by in the context of generative pre-trained transformer, or GPT, and generalization of that by other entities. You know all of them because they're in the news every day. And especially the influence that they have in the context of large language models and the interactions that they have in assisting us in many tasks. But I want to also highlight a particular development that has relevance to some of the activities in heliophysics, and in particular prediction and space weather. So about 2 years ago, DeepMind's weather prediction model, GenCast, outperformed traditional physics-based models anywhere in the world, and even other AI models in terms of accuracy and speed. So this is an area in which, for decades, people thought it would not be possible to use data primarily, that you need to add as much physical complexity in terms of governing equations and solving them in order to be able to, of course, in combinations with sensors, radars, satellite data. But this illustrates that if the data is rich enough and the advances in computation, both algorithmically and in terms of fast hardware, efficient hardware, it is possible to actually learn a lot from the patterns in the data in terms of prediction. Okay, so let me start at the very beginning. I'm going to talk about the focus today is on discriminative models, and what I mean by that is our models, building models that use supervised data, data with labels. Okay? I'm showing the example of image recognition or computer vision, because that's a lot of where all of these things started, but it doesn't matter. You can pick your interesting feature that you're trying to get to the bottom of, whether that feature exists in your data, in your solar application or data or not. So the first question I'm going to ask is just a binary classification. So let's start at the simplest case, and I'm going to add complexity to that model. So what's the basis of the problem? The question is, can we design an algorithm that will answer the question, is there a dog in this image or not? That's the setup. Or a cat, your favorite pet. So what's the formulation for this? Well, we have input data, which can be a value or a vector. And it doesn't really matter how you embed that vector. It could be an image. It could be a multidimensional data. It could have spectral information. It depends on the specifics of how you want to set up the application that you're interested in. But that's input data. And then we have an output or labeled data. So I'll show you exactly what I mean in the previous example. But the task of discriminative learning is that we know that there is a correspondence between this particular xi and yi. We have pairs of labeled data. And we want to come up with a model on an algorithm that you can call or refer to as an inference model or prediction model. Okay, so what is the task of learning? Well, The idea is we want to build, we want to construct this, what's inside this box without actually analytically coming up with a relationship between the input and output. So not explicitly, but implicitly. And the way that typically is done is by some sort of parameterization. We already do this, of course, for example, problems of regression and various problems. But the parameterization, in this case, is going to take on forms of, let's say, particular types of functions and composition of functions, composition of affine functions. And we'll get to that. So the task of fitting the parameters, of course, requires some computational optimization. And there are some important aspects of that I'll also talk about. And this is all based on a pair, these set of pairs of data that we have training. So what I mean by these pairs, first of all, before I talk about how this pair is generated or what are the issues related to that, let's just talk about why it is difficult for a computer in a traditional sense to recognize, identify, let's say, cat in an image. For a human, if I show you an image, immediately you will, unless it's really distorted, you recognize it may be an animal, but you can tell if it's a cat or not. The human cognition has the ability to abstract. But if you wanted to just write a computer program in a traditional sense to perform that task, what would you do? You would have the pixels, images, maybe a grayscale, maybe RGB, and essentially you would have to figure out how to process those pixels to come up with a description of the object of interest. But how do you tell a computer program what is a cat? Independent of thousands of variations on that theme in terms of size, shape, all of that. It's very difficult to specify explicitly. It recognizes based on just pixel descriptions of that image. So there's this notion of abstraction or generalization that our cognitive ability already is endowed with, but we want to figure out how we can do the same thing in terms of a computer. So here, you can see variations on this theme. This is the challenge. How do you write a computer program saying that, well, is this a cat or not, based on just at the pixel level operations, right? So we need to do something different, more sophisticated. Okay, perhaps just the fact that we have these variations and a lot of it, just like these 3 examples, if we have 3 million of such examples, is there a way that we can actually utilize that to be able to infer and predict further information? So what I'm going to talk about today is focus on discriminative models, which means that we have data that's labeled. The next 2 lectures, I'll talk about generative AI and generative machine learning approaches, where we don't have access to that XY pair, we only have X. And so the question then becomes, if we only have data without knowing what they correspond to, then how can we do anything with it? And the idea there is that this data that we are talking about is drawn from an underlying distribution to which we have no access. The probability density function, a multivariate distribution. And all of the ideas in generative AI are based on either implicitly learning that distribution, either directly or through some transformation to latent space. So I'll talk about that in the subsequent lectures. But today I'm going to focus on, suppose we have these different images, okay, and then there's label. That labeling can be done by human. Looks at it, says, yes, it is a cat. And you could, here it's just basically some corner pixels are marked as yes versus no. So somebody makes that label, but these days you don't actually have to have human doing the task of labeling. There's semi-supervised learning approaches, self-supervised, so it is actually possible to automate the task of labeling. But for now, let's not be concerned about how the labels are generated, but let's assume we have labels. So we know in these images, just by looking at the corner pixel, a computer program would be able to say, yes, there is a cat, no, there isn't. So far, that's what we're talking about, okay? All right, so what do we do? So in this case, if we have the label, no problem. We just look at, the computer program is easy, looks at the corner pixel. If it's white, cat. Otherwise, no. But what if when the new images come in? How do we utilize that? And so really the idea behind machine learning in the context of supervised learning is that there are mechanisms to search for mappings that generalize meaning go beyond the training pairs that we have in our training data. When the new data comes, they actually generalize, and by that what I mean is that you can actually come up perhaps with bounds on the worst case performance of how much error they will have in the prediction or the classification in those cases. So we're not going to talk about the very important topic of generalization just because it's beyond the scope. It's based on sophisticated ideas in mathematics and statistics using concentration inequalities to essentially understand what happens with the new data with perhaps the distribution shift comes in and what can we say about the quality of the predictor, the classifier that we're building. Okay, so let's first talk a little bit about the categorization of these machine learning and pattern recognition algorithms. They are classified, you can think of these categories based on many different things. Available annotated data, labeled data, and that's where the supervised versus unsupervised terminology comes into the picture. Complexity of model, linear versus nonlinear. I'm going to start today with linear and quickly generalize to more of a nonlinear model, both in terms of features and weights. Structure of output, independent versus structured. What do I mean by that? If I want to do a prediction, let's suppose on someone's height, so I can perhaps just look at some training data, a new subject comes in, and I'll be able to predict perhaps the height. But there are correlations. If, for example, if it's height and weight, we know that there is correlation between them. There's no reason for me to want to do prediction on each one of those features independently. Perhaps I can take advantage of the structure that exists in multiple aspects of that prediction. And this is, of course, very important in all of the functioning algorithms around us. So the notion of structured prediction is, for example, very important in some examples that you saw earlier on for, let's say, a sentence completion. You saw that example. When you're typing something and you want to figure out an algorithm, what are possible next words that complete that sentence, the whole idea of the fact that there are correlations, not only a sentence, let's just think of a word, okay? If there's a Q, the likelihood of Q being followed by a U is much higher than a Q followed by an X in the English language. So that all of that information is the underlying structure that is taken advantage of when we talk about structured learning, okay? Independent versus structured. And of course, the modeling of the data, which I already alluded to. Okay, so what are the main components? We have an input. You can denote it by an X. And this is typically just a vector defined, let's say, over n-dimensional vector defined over the real line. A discrete output. So first I'm talking about a discrete output. This is important, even though when I talk about regression, the output is not discrete. It's a continuous function. But this is a discrete output, meaning that the simplest case, a binary output, so the set of possible outputs is 0, 1, or negative 1 and 1. And a decision function, or a classification rule, which is at the output, it's a function of the input that we have. And so the main problem is, in pattern recognition, is to construct this decision rule, that F. How do we learn this function F that would allow us to, if new data comes in, I'll be able to map it to the corresponding output. So let's start simple. Linear regression, we talked about it yesterday, so I'll go through it very fast. But I want to talk a little bit just to make sure that the notation that I'm going to use heavily, it's fresh in our minds. So I'm talking about a vector X. Even though I'm writing as a vector, it can, as I mentioned, embed any n-dimensional data. The two-dimensional data, it just means that you have this lexicographic ordering of the horizontal and vertical directions. So we're not losing any generality there. We have a matrix. Again, this is n by m. we already defined what we mean by a norm, in this case an L2 norm, or essentially a notion of distance in Euclidean space, distance between the two vectors. And I don't need to talk about the simple notations. I'll also talk about some concepts that review or utilize some notions on the introductory probability. So for example, concepts such as a distribution. This is a discrete distribution, which corresponds to a probability mass function to characterize that. In the continuous case, it's a probability density function. And this is the abbreviation. Probability of the random variable takes on a particular value. Okay, in this case, it's the values that it can take. It's discrete. And since it's a binary classification, it's either 0 or 1. So essentially, it's a discrete random variable that's distributed according to a Bernoulli mass function, probability mass function. And the expectation, of course, is by definition, in the case of discrete, it's just multiplying a function of that random variable with the probability and summed over all of its realizations. In the case of continuous probability density functions, this is, of course, the most common one that I've already used. The Gaussian density, the mean, or the expectation operator, as I write it, is just the product of the probability and the random variable integrated over all of the values that it takes, the variance second order moment. And this is something that, again, is going to be important in our formulation, which is this multivariate continuous probability. And what this means is that we're talking about a joint distribution, okay, in this case, an n-dimensional joint distribution. So we can't treat them as the product of individual distributions unless they are independent, right? In general, we can't assume that that's the case, but we will invoke that assumption in order to be able to do a lot with it. And I just want to draw your attention to that. And this is just a generalization of the Gaussian density, where now you have the determinant involved, but the notion of essentially the variance becomes a covariance matrix. Okay, and a couple of things that I don't need to spend a lot of time. It's just just some vector algebra and how, for example, for a multivariate function, if you take partials, what sort of algebra comes into the picture. I'll leave this as an exercise, or I think if you use these types of properties, it just immediately comes natural to you. But the reason I've listed them here is because I'm going to use them for a few derivations. Why? Where does this come from? Is because we're going to need to compute partials in an algorithm, the de facto algorithm for a lot of machine learning applications known as backpropagation, where through successive applications of chain rule, you connect. Essentially, you want to search, you want to find the minimum, so you need to compute gradients, and those gradients are computed successively in a recursive fashion, okay? So that's really the building block of a lot of what we do. So that's why it's important to just have these properties fresh. Okay, so let's start simple. Linear regression, we've already talked about it, and you can imagine that we have some scattered data here. And given the outcomes, and by the way, by this data, I mean, in this case, what we have. Remember, I started talking about the task of binary classification, but I'm actually switching back to a case where the output is not just a discrete two-element vector. In this case, when I talk about regression, the output is just essentially defined over a real line because I have all possible slopes and all possible intercepts that I'm solving for. But how do I do binary classification on it? Is after I have completed my regression, then I draw a threshold. And that threshold, anything above that threshold, I call it class 1. Anything below, class 0. It's almost going and using a sledgehammer for the task, and then simplifying it back to just task of a threshold, okay? So it may not be natural, but I just want to start simple, and we'll see why we can essentially do something a little bit more relevant and appropriate for our task here. So regression, we all know what that entails. So the simplest case, if this is a scalar, we have just essentially just two weights. Remember, I said that in the function in between x and y, we want to learn parameters of that function. In this case, of course, we're starting with a line. There are two parameters, w1 and w2. We have a data set of n pairs, and I'm going to denote it in this fashion. And of course, we know how to compute parameters w1 and w2. We want them to be small. We minimize the distance between each one of those parameters, and we sum them up, and that's how we define the error. You remember I showed you that essentially these green lines, the sum of those is what we're minimizing, right? Okay, how do we write it? Well, in vector notation, you have the data, you have essentially the vector of the output y, and so this is, remember, we have access to y and x. This is labeled data, the pairs. And you write the set of essentially this x, which is written as, and so if r is of dimension, if y is of dimension n, x is of dimension n times 2, because we have essentially the ones. We have two parameters over here, so we have the extra ones. You just do row by column multiplication, and it's just another way of just writing this expression in vector matrix formulation. And all we have to do is essentially minimize this quantity, and with very little algebra, all you do is just you expand this vector, transpose times itself, the inner product, you go through algebra, and you just take the partials with respect to w. The w is what we want to minimize, and it's a simple algebraic equation with a few lines. You solve that, and you end up with, essentially, this is the derivative with respect to x. You set it to 0, and you obtain a solution that gives us this set of normal equations. We went over this briefly. So this is a result you might get, okay? And what we will do is we can generalize this to higher dimensional problems. Instead of a line, now we can essentially generalize this to any arbitrary function, maybe in terms of a polynomial, okay? First of all, that was a scalar. I can generalize that to a vector instead of a scalar. And I can generalize it to higher order polynomials with the same exact formulation, and I won't linger here too much. The point that I want to emphasize is that it doesn't really change the operations or the algebra. So all I have to do is, instead of just having two weights, w0 and w1, I have essentially this d plus 1 number of weights. And it's the same exact minimization problem, and everything just becomes a vector in this case. It just changes to a vector. And here's an example of doing the same thing. Instead of just that one-dimensional problem, now we're talking about a plane. Just increase the dimension by 1. Okay, that's the data. I want to fit a plane to this data in this three-dimensional space. And the question that I have for you is, what happens if n is less than its dimension d plus 1? In other words, what happens if I have fewer equations to specify than the number of unknowns? More degrees of freedom. What do I do in that case? How do I reduce the dimension? This goes back a little bit to yesterday's review of some linear algebra concepts, right? So I have an underdetermined problem. Fewer constraints than unknowns. So if I have an underdetermined problem, that means that I have infinite solutions, right? So I have to pick one. The typical way that you approach that is you pick the one with the lowest energy and minimum norm solution. Or if you have the opposite scenario where actually n is larger than that number, then you have an overdetermined problem, more constraints than unknowns. So you don't have an exact solution. You come up with an approximation just the way I talked about it. But if you have noise in your measurements, you may want to have some stability in terms of a side constraint to minimize the energy or the norm of the solution, okay? All right, so that's what I'm referring to. We talked about this a little bit in a probabilistic term. You have the the cost function that consists of some residual error plus a term that essentially stabilizes the oscillatory potential behavior. It just regularizes the solution. And if you write it analytically, it doesn't change anything, because essentially all you're doing is that you have this parameter C times I, so you're adding an identity matrix to the original ill-conditioned X times X transpose, and that essentially improves the conditioning of the original matrix. That's another way you can think about it. Okay, what about polynomials? Well, I'll generalize to higher order polynomials by just writing the same exact formulation, y, in terms of the weight. This is a second order polynomial, the first order term, the 0th order term, but I can generalize it to any degree polynomial that I want, and the exact same machinery can be written. Now I have, essentially, I can write this phi, which is a function of x rather than x itself, okay? And the dimensions are n by m, and then I have a vector of weights. But then again, if you just go through the exercise, you'll see that the structure of the solution is the same. You end up with a set of normal equations, except that instead of x itself, we have functions of x, what are known as features, okay? And let's look at an example. So I'll ask you a question. So you have, this is the same scatter plot that I had. I have the red fit to it, which was the linear fit. And then I have something that I think it's maybe on the order of 10-degree polynomial to that fit. Which one do you prefer? Most people prefer the line. It looks like they're going like that, right? But in this area, the black line does much better than the red, right? So I guess what I'm telling you is that I'm setting you up a little bit. I'm asking a question that both answers could be true. It depends on where you're looking and what you're looking for. So you're looking at the problem of this overfitting, because essentially, by the fact that you're assuming your assumption that the solution resides in a higher dimensional space, this high degree polynomial, perhaps is something that requires some underlying a priori notion of what you expect in your functional form that you're assuming for your fit. Okay, so let's generalize everything that we talked about. So now I have a function of this input data, and I have the outputs, I have the weights, I have the solution, and I have essentially this phi is a vector of all functions of x, any function, by the way, in general. It doesn't even have to be a polynomial, because later on I'm just going to talk about a particular class of functions, these nonlinear activation functions that are used in neural nets. Okay, so far we have talked about this deterministic, essentially vector space notion of what an error is in terms of a projection. But we can also think about the problem in a probabilistic fashion, and the reason why I want to do that is because it will allow us to perhaps do something a bit more sophisticated. So what's the probabilistic view? Well, if I am, these are the sampled data points that I have, okay? Sample data points. And for each one of them, I can think of them as being a sample drawn from a Gaussian distribution. And what does that mean if that's the case? How does it correspond to the formulation that I had? If each sample is drawn from a Gaussian distribution for each data point, okay? In other words, each one of these data points, if depending on where they are, what changes? The mean of that Gaussian changes, right? I'm already assuming that it's a Gaussian. And of course, there's a corresponding dispersion, sigma, but that mean is, the location of that mean is given by what? By the weights, the generalization of weights times this phi, the function of x. Depending on what values they take, the peak of the Gaussian shifts according to that, right, for each one of them. Now, if I wanted to model this probabilistically, and I have n data points, I have to go back and look at a multivariate n-dimensional Gaussian, jointly distributed together, right? That's basically what we have to do, which is typically not tractable. So what do? If I have this model, which is a multivariate Gaussian, where the mean of that Gaussian is basically given by the product of weights times the data points or functions of data points. I invoke an assumption that these samples are drawn, first of all, from identical distributions, meaning that they're all drawn from the Gaussian, and they are independent of each other, meaning that how one data was generated is not influenced by another data point that was generated. And in which case, what does that allow me to do? What's the most important thing that that assumption gives me the freedom to do? If I have a jointly distributed two random variables, okay, if they're independent, what can I do with writing that joint distribution? Multiply the individuals. So if it's density of x and y, I can write it as density of x times density of y. And so you generalize that, and essentially what that means is that allows me to write that joint distribution as the product of individual ones, okay? Remember this likelihood function that we talked about before. And I want to maximize this likelihood, essentially this forward model that best explains the data that I have over here. And so basically I can write this as a product, and the product becomes essentially a very simple, it takes on a simple form. I write it in terms of the norm. And it's an exponential. I want to maximize that. I can minimize essentially you remember a few intermediate steps. You take the log. You can take the log because log is a monotone function, so it doesn't change the optimum point in that function. And so I can write this in terms of just the following minimization, which again takes on that familiar form that we have seen so far. Okay, so that's good. So I perform my general regression, and now I want to do classification. I'm going to come back and try to do classification, a binary classification. So what do I do? So this is a line I fit. This is a bunch of data points. Remember, because I assume that it's a binary classification problem, what you're looking here is just a bunch of data points with some spread here, and then a set of other data points over here. Okay, I use this data, and this is the line that performs the regression for me. This is the result that I get. And I have a threshold here, okay? If I have this threshold, any the new data that comes, if it's on this side, I call it belongs to this class. If it's on the other side, I call it to the other class. Essentially, I do the full regression. I get the values of that parameterization of the function, but then I draw a threshold. And as we saw yesterday, there's an issue here, because if the new data comes and I want to train on that new data, and if the data I know a priori that it's error, outliers, what happens is it changes that line and it messes up the threshold by which I'm going to perform future classifications. So there's a limitation, and I want to do something better than that. And why? First of all, before I tell you first of all, if I want to do something better than that, just conceptually, the first thing that we can think of is that there's no reason for me to just try to fit a line first and then draw a threshold. Perhaps I can, if I know a priori I have two classes, I should do something different than regression, right? But why? What is this issue with the fact that I end up fitting to outliers, to errors above all in the case of regression? That's a limitation of regression, right? The problem is with this quadratic loss. So first of all, let me show you in this figure what I'm showing you here. This step function corresponds to just ideal classification. That means that if the values are positive, I'm making all the correct classifications. If they're negative, I'm making the wrong classifications. Why? Because assume that my two classes are either 1 or -1, okay? So if the actual data point belongs to class -1, and I make the correct prediction and call it -1, it becomes positive. If the correct point is 1 in class 1, and I call it that it came from class 1, again, it's positive. But if I have a mismatch in my prediction, I make the wrong prediction, it will be negative, okay? So that cost corresponds to this. That means that for all the negative values, meaning the cases where I have misclassification, I want to induce a cost so that I penalize that cost, okay? And for the cases where I have correct prediction, therefore these positive values in my binary classification, I don't want to penalize anything, okay? So those are all correct predictions. So this is really what I'm interested in, but I can't implement that directly in my optimization because of this discontinuity. And regression, as we talked about, this quadratic cost, if you actually plot the values, you end up with something that looks like this. But look at the behavior. So that means that, okay, in this area, I can say that, okay, so it's promoting all of my essentially wrong classifications. It amplifies it. So that's okay. It's introducing a cost for negative classifications. But the correct ones, you can see that is also penalizing. And that's exactly the issue why you have to fit to outliers in the case of a. So in this case, even though I'm making the correct prediction, it's actually fitting to the outliers. And the reason why I'm writing this way is because I want to generalize this to the cost of a neural network as we build sophistication. So this form, I just want to linger on it a little bit. So this is my cost. This is the discrepancy, right? And I can just rewrite it in terms of 1 minus y because y is either minus 1 or 1 as just described in words. So I can write it in this fashion. And I have a function that's a function of the weights and the data points. And then more generally, I can write a function of the weights, the data points, as well as the classes, my prediction, the classes, in this case, 2 classes. And that's precisely what I'm writing here. It's essentially a loss between each class that I'm predicting and the product of these 2. Okay, that's the loss. All right. Okay, so how to fix this? Logistic regression. Remember, we just talked about the probabilistic formulation of the regression problem. And the idea behind logistic regression is that if we already know we want to do binary classification, there's no need to assume this Gaussian. We are not drawing from a Gaussian, right? Because the data is not going to just come from anywhere under the Gaussian, right? So we need a more appropriate distribution, such as flipping a coin, right? In this case, it's a binary classification, and which is governed by a Bernoulli distribution with probability p and 1 minus p. So probably a better probabilistic model is more appropriate for what our goal objective is. And here, what you can see is that the probabilistic formulation of the classification, if you have these 2 classes, can be accomplished by essentially thinking about the mean of that Bernoulli fed to essentially a sigmoid function, something that transitions from one class to the next with some continuity. So I can write the probability of if my class is equal to 1, given my data points, the conditional probability, the conditional likelihood, is this essentially 1 over 1 plus the exponential, the argument of which is going to be given by the same mean that I talked about for the Gaussian, okay? And since it's a binary classification, probability of the second class, where y is equal to -1, given the data points, is 1 minus the previous probability. If I just write this as 1 minus this expression, I end up with 1 over 1 plus exponential of the mean of that argument. And if I just write them together, essentially in the same similar way, I can just write it as the general likelihood function, this conditional probability, which takes on the analytical form of this 1 over 1 plus an exponential. And remember, I wrote all of this in terms of a function of the class, weight, and the data points. So what do we do with this model? I have a likelihood. Essentially, with this model now, I just came up with it just like I did. I had a likelihood with a Gaussian assumption. I have a likelihood where I have this sigmoid and the mean of a Bernoulli in the model. What do I want to do? I want to maximize that likelihood, as I have done over and over again, to come up with the maximum likelihood solution. What does it mean? I want to maximize this function. How do I do that? Well, this is my likelihood. I have a set of data points, again, with the assumption that the sample data points are independent and identically distributed. I can write this joint distribution, this d-dimensional multivariate distribution, as the product of individual conditional functions, probabilities, and then choose the W, maximize with respect to the weights that I have over here, to be able to essentially maximize the product of these individual data points, these distributions, each one of which goes according to the distribution that I just showed you. Okay, can we do that, by the way? If we just look at this. You remember, I had an analytical solution in the case of the Gaussian. Am I going to be able to come up with, how did I do that? I had a likelihood, it was Gaussian distributed. I multiplied, and I took the log, right? Then I had an algebraic formulation. I simplified the algebraic formulation. I computed the partials with respect to the weights, set it to 0. I found the minimum. That's how I did it. Can I do that in this case? It's not straightforward. Let's take a look at it. See if we can do that. So what's the model? This is my model. This is my likelihood. I take the, I want to maximize with respect to weights. That means that I kind of minimize with respect to negative log. By the way, this term comes up in a lot of these types of computations. It's known as negative cross entropy. That's the name of this, essentially, this term. Okay, so I'm minimizing the negative of that quantity, and the product becomes a sum because of essentially the fact that I have the log function, right? And I can combine all of this. So I want to minimize with respect to W. I have the sum over all the data points, labels, paired data points that I have, log of 1 plus exponential of this argument. So far, this is my minimization. And so the first thing that you would think of, just like before, I have to compute partials, right? I have to take derivatives. And just before I do that, let me show you. This was the form, the cost of the minimization problem for logistic regression. Now, this is the form of, for normal linear regression and for logistic regression. And again, just recognize that a function of the data and weights, a function of data, weights, and classes. And again, we have a similar function with, of course, a different formulation. And as before, we want to minimize the empirical risk. The empirical part means we have data points, access to data points X and Y. Risk means just the loss, the difference, the residual error. And we want to minimize the difference. And this L, for example, could be quadratic in a standard Euclidean space. So first of all, what does it look like? Remember, this is what I want. This is what I'm going to ideally want, right? Basically, suppressing all of my correct classifications, inducing a cost, penalizing my incorrect classifications, misclassifications. This is what I had for the case of the quadratic cost for regression, and this blue is what I get for this logistic regression. So you can see it's much closer to the behavior that I'm after, right? Essentially, all of the misclassifications should be penalized, and we don't pay a lot of cost for the correct classifications. Okay? So now how to optimize? Let me go back to the question I posed. Well, I have to take the derivative, right? The derivative of this log, you can write it, the sum, that's linear term. You take the derivative of the log, and you write it, you expand it, and this is the formulation that you get. You can set this to 0, but then there's no hope of an analytical solution. So this is where we transition into numerical ways of finding the optimum of this function. And we've already talked about it. Probably the most basic approach, and of variations of which are the most common ones as well, are essentially some form of gradient descent, perhaps steepest descent. Successive projections into hyperplanes where we slowly step down a function to reach the minimum, as shown in this picture. You know, you can imagine just being on top of a mountain when you go skiing in Colorado and you want to get down on a foggy day to the bottom, and you look down and you find where the first step is the largest derivative, and then you take on the next step, and then you follow that path in order to do the search over that function for a minimum. Okay, so and numerically what that entails is some initialization, since it's a sequential procedure. And whether that initialization makes a difference or not has a lot to do with the properties of the cost, the convexity of that function. In this case, it turns out to be a convex function. We have this log, essentially. And if it is convex, then it's not sensitive to initial conditions. But as soon as it becomes a little bit more complex, when you can't guarantee complexity, the choice of the initialization has implications on whether you're going to find the minimum or not. Your ability to find the minimum. Well, of course, there's another factor that even if the function is convex, there's one parameter that will have implications on whether we will actually find the minimum of that function or not. And that parameter is known as the learning rate, which is this alpha. In other words, what are our step sizes going down that path? If you jump too long a leap, you can actually miss that minimum and go to the other side. That's the idea. Okay, so it has to be small enough, but you don't want it to be too small because convergence will be slow. So that's the trait space. But anyway, essentially, all it is you have some initial values, you compute the gradient, and then you update the parameters and you repeat that process. Okay, and if you do things correctly and in an informed way, you can get reasonable answers, good answers. Here's an example of what happens when you do that. So you have here, this is your data points. You see that these are X's and O's, the data that's essentially coming from, essentially a binary class that we have. Does such a feature exist or not in our data? That's the type of question you would ask. And you can see that essentially this is what you get in terms of a threshold. This plots the loss of essentially the plane of the loss or the error. And these are the successive steps in that gradient descent until we reach minimum. So what if we have data that's drawn similar to the example I showed you with outliers? Suppose we have data, some of it resides here, some resides here, some resides there. This is the corresponding loss. Remember, for regression, just linear regression, the fit would fit to the outlier, okay? And it would give us results that are unsatisfactory, but whereas in this case, there's robustness. You can still see that regardless of this new data, just because our model was the appropriate model for what our objective is, we have robustness to outliers in logistic regression. Okay. What are the trade-offs? Just to summarize, well, for linear regression, we had closed-form solutions. It was based on a tractable Gaussian probability model, not too well-suited for classification problems. Logistic regression, well-suited for binary classification. We have a logistic probability model, but there's no closed-form solution, so we have to perform a computation numerically. Yes?
Maybe I'm missing something, but we use this word a lot, like identically distributed and independent samples, I guess. But when we started with the example of a cat, like a picture, right? And those pixel values, they are not really IID, right? Because the face of the cat has to be in a particular position with regards to its body. It can't be like floating around. So the data is like structured. So I'm wondering if we can use, so in the mathematical formulation of logistic regression, where you had this like feature matrix with all the x's and the ones at the end, so we cannot use those pixel values there, right? Like for that, we'll have to have something more sophisticated that can work with non-IID data, for example.
Yeah, so a couple of points. First of all, when you talk about, there's a difference between correlation and uncorrelated and independent. There are two different concepts. You can still have correlations, right? So first of all, the correlation that you're talking about is not from pixel to pixel. If the object of recognition is an image, it's one image to another image. And you could argue, yes, there is correlation. Unless it's white noise, you're going to have some correlation as long as there is a natural image with some structure in it. You're going to have correlations among two samples. But the idea for independence, the assumption, is that there is no systematic, so you can, in terms of the distribution from which those samples, the implicit underlying distribution from which that data for one image is generated, it does not influence how the data is generated for the other ones. And that's really the underlying image. Now, to the degree that that assumption is violated, of course, again, we can't just use it without understanding how we collected our data. What are the characteristics of our data? It's important to think through. I think what you're pointing out is important, to really think about whether the assumption is violated or satisfied before we do anything, but it's not an unreasonable assumption for many cases where we have data. Okay. Yes. Please. Yeah, so again, you have a correlation in time. But the correlation in time does not necessarily imply that the sample that I took today comes essentially, it's the same distribution that generates it, but it does not, you don't have to write it in terms of a joint distribution. You can write it as essentially independently drawn samples. That's the idea.
But I have a follow up on that as well. So with the time series data, we like you said, we could pick it up at a separate time, but something like if some perturbation happens at time t and it travels to like time t is equal to 4 or something, um, so the sample that we grab at time t is equal to 4 is not identical, right? Because something that happened before is changing or is like propagating in the future. So with time series data, it should the IID shouldn't hold.
Well, that may be true. It depends on what you assume, what that underlying distribution is. So if you, for example, if you assume the underlying distribution is a Gaussian, your Gaussian has some dispersion, some variance, right, and some mean, it is possible that all of a sudden you get a sample from 6 sigmas, right, in the tail. Very deviates from all the other ones. Maybe you can model the deviation in your observations that way, or you can generalize that to a Gaussian of mixtures or any distribution that would capture the statistics of what generates your data. So it's not necessarily always violated. It always depends on what your underlying assumption is about that distribution. A lot of times, in most machine learning applications, you don't really, so this is just introductory material, you don't really assume a distribution in generative AI. You try to learn that distribution. The foundation of all of generative AI is to learn an underlying distribution which you don't have access to. You cannot write it analytically, but you can hope that you learn it enough so that if you sample from it, from what you have learned, it will mimic all of the previous instances that led to the data generated from that implicit distribution.
Thank you.
Sure. Okay. So let's move on. I'm going to skip a lot of details because I really want to get to neural nets and deep nets. Support vector machines, they are, of course, conceptually they're important. In terms of utility, as you will see, the progression of what I talked about, logistic regression, support vector machine, a multi-class version of it, they're all essentially special cases of multi-layered perceptron models or deep nets. So that's why I'm introducing them, not in the sense that, yes, this is what you should be using, because if you have a sophisticated architecture that uses multi-layered neural nets, in a way, you have more generalization. You have less constraints in terms of your model, and your model has the ability to learn the features from the data automatically. But I think it's important to understand conceptually at least what this is. So I'm not going to linger on the how to solve the problems and the optimizations, but I want to describe to you the conceptual underpinnings. So the idea behind a support vector machine, again, in the context of binary classification first, and then we can generalize it, is that suppose you have these two classes. You have this is the data from one class. These three are the data from another class. And the simple case where actually if there's a linear partition between those two, which of course in real data there won't be, but let's start simple. I can draw a linear partition. So for the two classes, remember, I can write this weight times the phi, the function of that data x, to belong to one class, call that 1. Another one called -1. This line in the middle is when this is 0. So you can think of it as the 0 of that distribution, that middle of distribution we talk about. And you can easily convince yourself that the length of this distance is 2 over the norm of that weight, the W. This is what's known as a margin, okay? And the idea here, the idea behind support vector machine, is that we want to maximize this margin, so I can write it as essentially maximizing the margin means minimizing essentially this W, the 2 norm of the weights, with an additional constraint such that this product of the class weights and x is greater than or equal to 1. This is similar to what I told you. If I have correct classifications, it will all be positive, right? In this case. In fact, it doesn't have to be 1 as long as I have any L greater than 0. That side constraint will classify exactly what I'm interested in doing. Okay? And what if the data is not linearly separable? What if one of these x's is actually on the other side of the line? And the way, the machinery that's built in handling that is basically introducing something known as a slack variable, this zeta. And what that means here, if the x is over here, so I won't only try to maximize this margin, but the sum of that plus this, what's known as a slack variable. Okay, so basically I have the minimization of a term that corresponds to the weights for the original linear separation of the two classes plus this slack variable, and the constraint becomes, the side constraint becomes essentially same terminology, greater than or equal to 1 minus zeta, the slack variables. So this handles the cases where you can't draw a line, straight line between the two classes. The data is somewhat mixed, okay? And what does that give us? Well, for this case, we have a constraint optimization problem. I won't go through the details of it, but you can show that that corresponds to the case where this equivalent problem is that we still want to minimize with respect to weights the norm of the weight vector plus a term that corresponds to sum over all data points, maximizing 0 or a term which is 1 minus that function, capital F, of the class, the weights, and the data points. And if you plot the same function as I did with the previous ones, what that corresponds, so remember again, this is what we want. The red is the quadratic cost corresponding to linear regression. The blue corresponds to the log loss that corresponds to logistic regression. And the pink is what is known as this hinge loss, which corresponds to finding the max, this max function between these two quantities. And again, you can see the similarity, right, between this and the blue. It essentially gives us a good result in the sense that it penalizes all of the misclassifications and only has some error in the correct classifications that's relatively small. Okay? And the point that, I'm going to skip over a lot of details in the interest of time, but the point that I want to make is that these two are related. The hinge loss and the log loss. In fact, you can generalize it in terms of a more generalized function that in the limiting case of changing some of the parameters, the two become the same. Okay? So how do we optimize this? Again, gradient descent. The actual optimization corresponds to a little bit more sophistication. We can't just throw gradient descent at it because it's a constrained optimization problem. We have to invoke a concept known as duality. But anyway, these are the concepts that you can look up if you look at the textbook on optimization theory. So this is, again, a reminder. Linear regression, we had this cost, the quadratic cost. Logistic regression, we had this form. And for binary support vector machine, we end up with the following cost. And we saw the plot, I already talked about it. And this is what I was talking about, the connection between the hinge loss that corresponds to support vector machine and log loss is that if you just generalize these two in terms of a log of 1 plus the exponential of a general function f, and you look at the limiting behavior, which is epsilon as it goes to 0, you can show that the two functions, the two costs that I just showed you for support vector machine and logistic regression become the same in the asymptotic behavior limiting case. Okay? And again, without going through computing the limits and L'Hopital's rule and those kinds of things that bring us back to fun calculus times, the point to keep in mind is that a support vector machine is essentially limit of zero temperature limit of logistic regression. So the two are related. Yes? Are you saying that this is the blue or this one is not this one? Yeah, but it's not sure. But again, you can set up the admissible set in your search in a way that the endpoints don't matter, right? Where you perform your search is you define yourself, right? Because you're not going through infinite range of values. Okay, in fact, this plot, what the plot shows is that if you change those that epsilon values for different values of the logistic regression, you can see that it starts resembling essentially the support vector machine or the hinge loss, which is this magenta color. So you can essentially approach the two become the same. Okay. All right. I'll just talk a little bit about, okay, so remember, the progression we are interested in, this is a simple problem of binary classification. But in practice, if I want to go in the direction of function approximation, a general arbitrary function, you can think of it that every infinitesimal segments of that function, I have a binary classification to find the value, right? And as it progresses, I have this essentially all of the binary classifications, but if the function value is not just binary, it's within a range, then I have a multi-class classification, right? There are multiple classes, so the set, the discrete set that I want to solve for in my formulation is not just 1 and -1. It could be 1,000 different values or however many values make sense for that problem. So that's what's referred to as multi-class classification, okay? Where the output y sub I is not just a two-element set. Still discrete and finite, but it could be infinite actually when we go to function approximation, but countable. Okay, so multi-class classification, what does it mean? The question is how to classify between k classes instead of just two classes. Well, the simplest way we can accomplish that is, well, you can think of it one versus all or one versus rest. So in this case, you have 3 regions, and you can compare, do a binary classification on one and say, does my data belong to this class or this class? And then if it's in this class, you hold it, you keep it in this region, right? If it's in this class, outside at the other side of the line, and you can do the same thing. You can make a comparison between R2 and R3. Right? But then you always end up with a region that is not uniquely decided in that comparison. So you can use k-1 classifiers, binary classifiers, each solving a 2-class problem, which separates a point in class k from point not in this class, but you end up with essentially ambiguous regions, okay? More than one good answer or no good answer. You can generalize this. You can say, how do I classify between k classes? 1 versus 1. Use k times k-1/2. That's a combinatorics, which, by the way, this should look familiar to people doing aperture synthesis, right? The number of data points in correlating antenna elements in radio astronomy, in interferometry. Okay, so 2-way classifiers, one for each possible pair of classes. So classify samples according to majority vote. That you can generalize that. And that makes things better, but there's still some cases where are going to be ambiguous in terms of essentially doing the majority vote in terms of is it this, is it that, and you can go through the exercise. So but how do you generalize this to avoid this? You generalize it by essentially, instead of having these 2 classifier, which is based on this binomial distribution, right? Each one of them is Bernoulli, but you repeat those trials, it becomes a binomial distribution. You generalize that to a multinomial distribution, the formulation for which is written in this fashion. So you're looking at the likelihood of y belonging to an element in the class K, given the data points, and you write the corresponding distribution in a multinomial fashion. The bottom is just a normalization factor, and this is essentially the form of how you have devised the K weight vectors. Now, you don't have just one weight vector, but you have K of them already there so that you can automatically figure out the values of the weights that correspond to the multiple classes. So for each class, you're going to have a set of weights. And then you can decide which one out of K classes essentially gives you the best weights for your problem. And again, maximizing the likelihood is as before. You maximize things. In this case, you have K weight vectors with respect to W and negative log. This cross entropy term is what you're minimizing, and then you can solve it numerically, and that now we have a tool for doing multi-class classification. Okay, good. Now I'm going to skip through illustrations of visualizing how this multi-class classification works. Again, in the interest of time. And I'm also going to skip over how you can generalize what we talked about for SVM, binary SVM to a multi-class SVM. All you have to do is just introduce just slightly more complex model, but you can capture. It easily generalizes to multiple classes. Okay, I'll skip over the mechanics of those. There's one question that I want to address, and this is important in machine learning, even though we're not going to spend a lot of time on it. Notice that the cost function that we have so far in our current framework, it looks perhaps a little bit maybe daunting in terms of the terms that it has, these double summations, logs, exponentials, and all of those. But still, if you look at it, the sums and the terms are linear in the feature space. This feature space between the data points and the classes, the labeled data that we have, it's still linear, right? The way we fix it is through a notion of something that I won't talk about, but it is important. I think maybe I'll talk about it a little bit on maybe either tomorrow or Monday. The idea is to come up with a transformation into something known as kernels, where it allows you now to remove the restriction of things residing in a linear space through a particular set of transformations that are proper inner products. Again, you can read up on this if I think it's important. They're still used in many contexts. Let me just tell you that this is the idea. So many inner products, this is, remember, the feature space that we were talking about, between different samples. So basically what replace the inner products that are given over here to a call to a kernel. But of course the kernels, these predefined transformers, have to obey what defines a proper inner product. We don't need to explicitly construct the feature vectors. We just draw from these kernels as long as the kernels are valid inner products. Okay, that's the general idea. Here's an example of one. There's a whole bunch of other ones. You have a linear kernel, you have a squared exponential or Gaussian kernel, a sigmoid kernel, and so forth, and other ones. They're properties that you have to, essentially, these are the properties of a valid inner product. You can verify if a given kernel satisfies them or not. Okay, so for the remainder of time, I want to talk about finally building up to essentially what's used most, right? The most prevalent form of, like I said, we started with binary classification, we went to multi-class, and we want to see now how that multi-class allows us to do a universal function approximation. In other words, I have X as my input, the data, the classes now. Again, I have a set of classes, and there's an implicit mapping I called F that I'm not going to really attempt at finding analytically, but through a lot of essentially training data and optimizing for the weights, underlying weights, in a particular form, functional form of that function f, be able to find that mapping, learn that mapping. That's the general idea. Okay. So let's see what are the conceptual underpinnings. There's a reference here. The important thing that we need to understand is that there is a forward and a backward pass in a multi-layered perceptron model. Okay, so far, what I just showed you was something that captured essentially the form that we had for a general multi-class classification problem. That the specific cases, special cases of this could be interpreted as support vector machine or logistic regression, any of these classification techniques. And the possible limitation that we talked about, which was linearity in feature space, we said that, okay, we can use kernels, and that's an important class of techniques. But still, we are learning a model in this formulation that is linear, not only in the feature space, but in the parameters W, in the weights. And we would like to, for complex data, to remove that restrictive assumption as well. And that's exactly what neural networks, layers of neural networks give us. So in other words, look closely. This is very important. So we replace this product of the weight times feature space with a function that's a much more general. It's not just linear, okay? It's just in any arbitrary function. Function of, remember what I had, the weight, the data, and the classes. And that's really what we're after. So I'm going to replace this linear function in the weights by something that can be potentially nonlinear. And by the way, this cost function is exactly the cost function that you get for when you talk about layered neural networks. So what is the conceptual point, take-home message to remember is that deep nets are a generalization of multi-class approaches for classification with less restrictive on the model. It can be arbitrary and nonlinear. We still have some restrictions that I'm going to talk about because we need to be able to build something that's computationally tractable in terms of being able to find the minimum of that function. Remember, we want to maximize the likelihood and we want to minimize the negative log of that likelihood function. Okay. So what's the idea? The idea is the following. That we want to know what function, this general function, capital F, of the three weight, data, and classes we should choose. What properties do we want to have? I already alluded to the first one. We want it to be differentiable. We want it to be differentiable so that we can actually compute gradients and do a search. We also, so we build essentially, and we want it to be in a way that if we have layers with all these degrees of freedoms for a general function, we want to find a way where these differentiations using successive chain rules can be computed in a sequential fashion. Okay, and so it's computationally tractable. So I can write it, this f, as a composite function of essentially this F2, F3, and all of the other ones. These, by the way, correspond to the different layers in this construction of this sort of function. So functions can be represented in this fashion, as you can see, because of this composite form as an acyclic graph, which is referred to as computation graph. If you go to Python, a computation graph can be generated in the form of a forward pass for essentially the deep net architecture that you build. And this is what it looks like. So you have the general function. It's a composite function. You have weights for each one of those layers. Okay? And so you have a weight that is a part of this function, but also the composite means that the output of one function is the input of the next. That's essentially what that means. So what sort of functions? I talked about differentiable, but what else? Well, I want to show you that what the idea behind essentially an activation function based on a neurons, very similar to that sigmoid or the logistic function that we talked about in logistic regression, will allow us to do this partitioning in essentially a hyperplane in higher dimensional space that will allow us to find the values of the function. Remember, we want to do a function approximation here. So what are some examples of such activation functions? This is just a sine function. So you have this behavior, right? This is what we already use, this logistic function or sigmoid that has this behavior. This is what was used in the earlier versions of neural networks and deep nets for decades. In the last 10 years or so, these functions have become popular because they address a problem known as the diminishing gradients. When you have many layers and you propagate the gradients, the value of the gradient becomes so small that it's hard to find the slope in which direction you should be going. But anyway, that's a detail that we don't need to be concerned about right now. But this is what's known as a rectifier linear unit, or ReLU. And because of this discontinuity at the origin, there's a variation of that known as leaky ReLU. So at this point, it doesn't matter the specifics of it, but the fact that we have essentially this activation function, okay, for each one of the nodes. But how is it used? So let's look at the here. These are our data points, x1 to xn, at one layer, fixed layer. Each one has a weight, and then we have a bias term. So, and then I pass that into this activation function, this nonlinear function, any of the ones that I showed you in the previous page. What does that mean? That now I have a sigma of W transpose X plus B. Notice, what sort of function is this? If we didn't have the B, it would be a linear function, but we have a bias. It's what's known as an affine function, or affine linear function. And that argument is passed into this activation function, okay? So why do we do this? Well, let's look at that. And this is just a simplified representation of the same thing. Here's the reason. Notice that, look at this picture, figure over here. This is the line in the case of just a simple plane and a line where W transpose X plus B is equal to 0. Okay, what does that mean? That means that if I change the bias and move it around, I have a way to partition, do a binary classification on this plane. Okay, we output +1 if WTX is greater than B, and -1 the value of the class if this is negative. So which side of this line? With the same exact model that I just showed you, this affine function. Right now we don't have composite functions, just one function, one node. Okay, this is just one neural net. Now the multi-layer neural nets, because of the composite aspect of these functions, where the output of the first layer is input to the next layer, allows us to divide high dimensional space in ways that allow us to approximate functions for mapping inputs and outputs. And this is really the underlying idea of how these deep nets are used as function approximators. And of course, you're going to see some examples of that this afternoon. And by the way, I'm talking about the general building block for deep nets, but they are really themselves building blocks in terms of variations in architecture for things, for example, like transformers, which is, I guess, again, the foundations of large language models, these types of things that you see. There is more complexity under them because there's also the element of either time or correlation in space and time and those types of things, and there are multiple of them used in building blocks with more complexity. But this is really the unit, the unit that is at the heart of a lot of what you see around you. Okay, so let's look at what I meant by layered version of that. So far I was only talking about one node. This is the activation function, and this is a set of inputs, data inputs, that's fed into the activation function, and we have, these are all the different sigmas, and the output, again, is passed in a similar way to the next layer of that network, and so forth and so on. And that's what is known as a multi-layer perceptron, and depending on how many of them, you can call them a deep neural network architecture. So, first of all, a few points here. Number of neurons in each layer can be different. All weights on edge connecting layer, the previous layer, and the next layer are in a matrix form, so that we can write all of the weights in a matrix. And the same thing, we can include the biases in those matrices. And there's an input-output relationship, so you can write it in this fashion, okay? And you can write it compactly in, again, vector matrix form. And this is the feed forward. So at the heart of every deep net, when you actually run it, there's the two steps. One is the forward pass, which generates a structure of how many layers you have. That forward pass generates that computation graph. And the second pass is what's known as back propagation, which means that you essentially compute these partials and feed it to a gradient descent to solve for the minimum of that function. Okay, so again, let me just tell you, I'm not going to, I leave the slides for those of you who like to go through it once and convince yourself of how this sequential backpropagation works. But essentially, it's just done layer by layer. You start from the last layer, which is the output of the deep net, and you connect it to the previous layer, and you pass the partial with respect to each one, and then all the way to the input. And one more point that I should make is that a lot of these things you don't need to, I'll show you the algorithm, but you don't need to implement, right? For example, there is a very sophisticated auto-differentiation some of you have used in Python libraries that you can use. But so just conceptually, let me just briefly show you what we're talking about. So conceptually is that we want the output of the neural net to approximate some desired function. And this is what I mean by the function approximation aspect of the problem. What does it mean? That the last layer, the output y hat, which is the mth layer or the last layer, we want it to approximate some function f of x, y. Okay, so this is specified to us. Where do we get this? Remember, the labeled data, pairs of y's and x's. That's the training part. So how's the function approximated? We use labeled training data, inputs for which we know the correct outputs. Okay? Even though the function itself is unknown. So this is conceptually important. We don't know the function. We're not going to learn the function explicitly. But because we have training data, we implicitly learn the mapping, that f function that generated y from x. And so what's the idea? We minimize an empirical loss or empirical risk on the training data. What does that mean? Some difference between the y's that we observe and the y hat. So remember, y hat was the output of the last layer. Okay. We have access to the y. This is part of the labeled data. Y hat is the output of the neural net, and we can just essentially successive differentiation will allow us to find how to minimize this function, this empirical loss. And what it entails is that we have to compute these partials with respect to weights and biases, and sometimes you can actually combine them so that they're essentially in the same vector when we compute those. I'll leave these details, steps for you, but essentially all it is just successive applications of chain rule. Okay? And there's a recipe, and for backpropagation, essentially, this is what the summary is. You compute the partial for all of the i's, and you start from the last layer, and you propagate to the next layer, where essentially these partials with respect to yi's are given by, again, a summation over the derivative of the activation function times the weights and the partials in the previous step. Okay. Like, as I mentioned, auto-differentiation, already, you don't need to actually call this up. It gives it to you. Okay, so for the remaining minutes, what I want to tell you is that there are so many variations on this theme. I try to emphasize just the conceptual underpinnings so that we understand how this multi-layered perceptron can be used as a universal function approximator, starting from very simple classification tasks. However, as you can imagine, this is a fast-growing area, and over the last 10 years or so, there have been so many variations on this theme, and most of those innovations are responsible for why some of these systems are so powerful in terms of the results that we see around us, especially in certain applications. So what are some of those architectural variations? Well, I talked about essentially what's known as fully connected layer, meaning the output of each layer is input to the next layer, but usually we don't do that. Convolutions, instead of just basically connecting those layers, I'll show you an example. We perform convolutions. It reduces the feature space of the functions, and it has relevance to cases, for example, when we are working with images or time series data. For images, one of the properties that we want, for example, for automatic recognition or computer vision, is that we want to be able to recognize images that are translation invariant. So displacements will not change our ability to recognize what that image is. And so this convolutional neural nets accomplish that. I already mentioned the rectified linear unit, which allows us to be able to compute those gradients more effectively. So when they diminish as you go all the way from the last layer to the first layer, when you have many layers. And there are other ones. Dropout corresponds to the case where you don't connect everything. You randomly disconnect, or you set some of those weights to 0, and this has some desirable properties in terms of not overfitting to data, for example, as well as reducing computation. And then here's an example of one of the early examples that goes back to 1998 by Yann LeConte. You probably have seen some of the work. Awarded the Turing Award with others who initiated a lot of the early developments. And this is an example of where you start. So you have this is just one image. Of course, you're training on many images in your data. And the input layer performs a convolution. So a convolution, in this case, in 2 dimensions over the image. And you extract that feature. And as you can see, in the convolution layer, you decrease spatial resolution because that's what convolution does. It's a smoothing operator. But then you increase the feature map, the number of feature maps. So a convolutional neural net has the operation of the convolution on your data. It doesn't have to be images. It can be time series, because you can perform convolution in any dimension. And what it allows you to do is to extract these features. Now you have, depending on how you change the parameters of the convolution, for example, the width of your convolutional mask. How many pixels are you using in your convolution, that kernel? That allows you to essentially reduce spatial resolution, but increase the feature map. And then you move essentially by this subsampling layer until essentially you increase the feature map, reduce the resolution, and then finally you end up with the output. And so this is one of the early demonstrations of how these types of architectures are quite effective and powerful in computer vision. Here's another example. They're structurally simple in that a layer's output is used as input for the next layer. But it's not a requirement. This is a fully connected layer, and there are, of course, issues with that for many reasons, because of overfitting, but also in terms of computation. For example, if we have an image, suppose we have just a very modest resolution 256 by 256 image. Okay, that means 2 to the power of 8 times 2 to the power of 8. Okay, that's the input, and the output would be another 2 to the 8, 2 to the 8. So you end up essentially the number of weights that you need is 2 to the power of 32. So we can't work with that, and that's why there are many ideas about how to handle this, sharing the weights with convolutions, for example, do some maximizing or averaging, essentially functions that reduce the number of this propagation that are needed. And I won't go through all of them. Those are details that become important if you work on some specific things. This is an example of a dropout I mentioned. As you can see, it's not a fully connected layer. Some of the weights are set to 0. Not only it takes care of the computational bottleneck, but it also, this randomization allows you to get solutions that don't overfit and they don't get stuck in a very undesirable local minimum. Okay, let me stop here. Let me see, is there anything else that, no, this is just a summary. Okay, let me just stop, and this is a backpropagation. I already talked about it a little bit. A little bit of just summarizing some connections. A deep net with a single fully connected layer is equivalent to logistic regression, something we've already seen. Okay, what is the advantage? Why are they so much more popular than things like logistic regression, support vector machines that 10, 15, 20 years ago you would see a lot of work on them, but they're all replaced? Is because it essentially, because of the fact that you don't need to handcraft features. You actually automatically extract the features from the data. And well, the disadvantage is what? They're computationally demanding. You need, well, we all know about that. And people talk about the power impact and all of the hardware that's needed, the computation, the GPUs, and whether that will scale in the future or not. And they require significant amount of training data. So it's important to not just throw it at any random problem, but understand the specific problem that you're working on to see whether what is, there's one fit all. There's no such a thing as one fit all. You have to really understand the characteristics of the specific problem you're interested in solving in the context of function approximation. So, but why are they so popular? Well, we have better computational resources. We've had it in the last 2 decades or so. We have a lot more data. We have more sophisticated algorithms. And most importantly, it's hard to argue with success. I think even people who were hesitant and conservative in using things, once they go to a large language model, they realize that, of course, it has issues, but it also has a lot of impressive results when you work with them and the kinds of things that it can perform. Okay, so let me stop here.
So if I use just one neuron, is it the same as a support vector machine with some kernel similar to the activation function?
Yes. Yes.
Is it like straight up equivalent or there is some difference?
Well, it's very close. Depends on the specifics of how you remember I said that a fully connected layer is essentially a logistic regression. And support vector machine is, again, you can think of one being as a special case of the other one, right? So there are some tuning parameters in each one of them, and if you have the appropriate tuning parameters, they're identical, essentially.
In your view, is there any use for these older methods like SVM, stuff like that, or should we all be using neural nets for everything now?
That's a good question. It really depends on how simple the problem is. If you know that you just want to do binary classification, there were groups, by the way, in previous schools where, for example, they wanted to look at some data and ask the question, is this a switchback or not, right? So it's a very straightforward binary classification problem. So you don't need to throw a 20-layer deep net at that problem. It's not necessary, and maybe it even might confuse things, right? So a logistic regression is a perfect model for answering that sort of a question. So it really boils down to ultimately what the objective is. And I should also mention that this is one of those areas where there has been a lot of attempt by a lot of good people with deep analytical skills to try to analyze the properties that some of these nonlinear composite constructs can have and try to essentially characterize their performance, not empirically, but analytically. And it's an open problem. It's a very difficult problem. Okay, so a lot of innovations and results that you see in the literature where the action is a lot of it is just by empirical innovations. They have an intuition. So a lot of intuition actually goes into the type of architectures that you would build. So that's another thing that I should say. I think, let's see, Tim referred to it in the context of inverse problems as a black art, and it certainly is the case in this.
So say that you found a problem where you think that this might be a promising approach. I think we're looking at some of the capstone projects and kind of coming up with that idea. I guess you that maybe have a little bit more experience, there's the whole zoo of, different architectures, like models, and even within one model, right? Like there's many moving parts that you can change and adapt. So how have you been able to maybe grab something that you've seen in a paper or something and adapt it to a problem that you're interested in? How does that process look like?
Yeah, that's a great question. I don't think there's a universal answer to that. I can share with you my own personal
Yes,
approach.
I kind of want to hear.
I prefer to go down the path of toil, hard work, and really learn under the hood. And what are the assumptions? What are the conceptual motivations for a development? I believe that makes a difference in being able to use a tool correctly. But I can tell you that in any application domain, regardless of whether it's heliophysics or any other disciplines within science or even outside of science, that may be too demanding because it requires investment in time. We're all doing other things as well. So a lot of people, they just try to get a recommendation, say, try something and see if I get something meaningful or not. Personal preference is not to take a shortcut. Not to take a shortcut. Go down the path of toil if you really want kind of work where you can, when we get a PhD, one of the things that is expected, you stand in front of an audience, you're proposing either an idea, a hypothesis, a method, or whatever it is. The expectation is that you will be able to defend that this is the way. It's not a way that I'm choosing to do this, but it's the way that it should be done. Everyone should be thinking at it this way or should be doing it this way. That's the expectation, right? That's in the ideal case. And that requires really getting to the bottom of things and not just, pulling something off the shelf and just trying it. It's okay to do that, but not stopping there is what I'm saying.
You talked about convolution, right? So the last example you told that we have to choose, like suppose we need to identify some features of a picture, some pixels, and we reduce it so that we identify some coarse features of that. So I just want to know how you fix that, how many pixels you have to choose, and what decides the percentage of reduction you do. Like how much percentage of reduction you have to do in the next.
Yeah, again, that falls into the category of a lot of intuition and looking at what other people have done, why they make those choices, and what they reported. But in general, the guiding principle is that, so you have an image, and your convolutional kernel, first of all, what form should it have? Is it a Gaussian kernel? Is it a rectangular kernel? The actual form of the convolution kernel, just like just a standard instrument. A Gaussian kernel for a convolution, a rectangular, circular, or whatever, all of those types of things, right? So there's that choice that may or may not play a role in the specific problem that you have. The second one, which is probably, I would say, more relevant to what you're saying, is that the larger your convolutional kernel, the mask over your images, for example, what does that mean? That you have reduced the amount of data you're dealing with, right? Because now you have, by the way, it's not just the size of the kernel, it's also the amount of shift. Do you shift by 1 pixel or by a range of pixels? And how many times do you do that to get the feature? So all of those are essentially choices, right? But the trade space is that if you have a larger area and longer shifts, you produce, essentially, you can produce more in the next layer, more information in feature space. You're extracting the information, the underlying information from your data, but you're losing high resolution information. So it depends on what your application is, but that's the trade space.
You mentioned the issue of overfitting. Did this refer to the number of layers or how the weights were connected? And in practice, can you estimate when this overfitting might appear so you know how to avoid it?
Okay, so what we mean by overfitting is fundamentally no different than when you do overfitting in the simple case of linear regression that we talked about. Overfitting means that you have too many, let's say, too many constraints. You can think of the overdetermined problem, which means what? You have more equations than unknowns. That's essentially what we mean. Too many constraints. And those constraints, remember what the form of constraint, the loss looked in a layered, multi-layered perceptron. You have data and you have a pair, labels, x and y's. And if you have a lot of those, and if you weigh all of them the same way, and you do it in a way where there's emphasis in your search for the minimum, uses a lot of that specification, then that means that if some of your data is out of that distribution that you're looking for, you're going to fit to it and you're going to get results that don't make sense. And so how do you look for it? The last part of your question is you look at it and you see that essentially it's not approximating the function that you wanted to approximate. So you can always do tests like that. And it's fitting to essentially out of distribution data. Now, what do you do about it? There's a host of different ways of making sure that you don't have overfitting. Essentially, you have to regularize the problem. We talked about some of that in terms of a side constraint, but also the fact that if you asked about the weights, if you don't use all of the weights, if you set some of them 0 so that you have this what's known as a dropout, okay? So not every output of every activation function is led to the next layer. That is shown to essentially avoid this overfitting because essentially you're dropping some of these, you can think of it, more constraints that you would have. So that's one way where you can avoid that overfitting.
Going over here. And then yeah, we can also then open it up to questions for Tim.
I just have two kind of related questions. So one is like when we use like the L2 norm as a cost function for these deep neural networks, we assume that the sampling distribution from which we are taking the data is essentially a Gaussian. So like, do ever people assume like if there are other kind of systematic errors that are there in my problem, I could have a different kind of a distribution from which it is essentially sampled. So do ever people like assume the other kind of distribution functions which can lead to different kind of cost functions in the problem? And the other question is like, essentially our problem is not just to minimize the in-sample error, it's also to minimize the out-of-sample error. So is there, apart from like looking at different situations where we see both of these errors reducing, is there like a mathematical framework which can show us that bounding the in-sample error does lead to a bound on the out-of-sample error as well, which is the essential problem of generalization itself?
Yeah, so your second question is a hard question to answer. I'll comment on it. The first one that has to do with, are there other types of costs? Remember, we wrote the empirical loss as a general function. So yes, it's your choice, and the choice again has to be justified just like the way you did. If you have the quadratic cost, the advantage, the trade space is that the optimization problem becomes more manageable. It becomes a more tractable optimization problem where you do your function search for the minimum. As you go to other norms, that changes. But for example, if your solution resides in a sparse space, then you may want to use something that's different. You may want to use something that's an L1 norm rather than an L2 norm. And people, if the question was, are such things are used? The answer is yes. But then it gets to a point where the optimization becomes so difficult that the problem is not going to be tractable computationally anymore. So that's the trade space. The second part of your question is about generalization. Are there results in generalization where they put bounds on not in-sample and out-of-sample errors? And the answer is yes. As you can imagine, just because every year there are hundreds of conferences with a lot of good people and good results, very fast moving out there, yes, there are. The issue with generalization error doesn't matter, in-sample, out-sample. In general, the bounds that people come up with, they're elegant. But for a lot of practical applications where you have a lot of data and it's very hard to characterize the data, the generalization error bounds using concentration inequalities are not tight. So they're the worst case, and they tell you something, but that something is so far from the region that you want to be able to see some results that are useful So I would say there's a gap between the bounds put by generalization error, but versus what people use in practice.
So, if I understand correctly, we did not use linear regression for because it gives multiple values for even for binary classification, but for a multi-class classification where we need multiple values, can we use a modified version of linear regression, such as using hyperplanes in dimensional space?
Yes, so the idea of regression is that you have a parametric function fit, which is what we all do, right? That's something that we've done always. So you have a parametric model, like for example, a polynomial to some data, and you model it that way. And now, if you want to do a classification, the next step is some sort of a thresholding. So you have to discretize that space that you have fit in the parameter space. And if you have multi-class, sure, you can have, for example, a binary or maybe 4 classes. Then you have to do that thresholding at some point and then make a decision. And you can do that.
Yeah, so I was curious about specifically for the case of gyrosynchrotron radiation from active regions. If you want to reconstruct the magnetic field, are there ways that you think we can reduce the degeneracy of the problem?
I'm sorry, I missed the first part of that.
So for like looking at if say you want to reconstruct the magnetic field in an active region from the gyrosynchrotron radiation, are there ways that you think we can reduce the degeneracy of the problem do that better?
Yeah, so you're referring to the thermal gyroresonance emission where we see the shells, the isogauss contours?
Yeah.
Yeah. Okay, well, as I mentioned, that's sort of a frontier problem, and there's notably working on the forward modeling aspects. But, you know, it's a complex problem because in order to do it properly, you really need to know temperature in order to extract magnetic field. Now, some ways that might help a little bit with that, assuming you have a stable active region, the sun does rotate, and you have a very high sensitivity to the aspect angle relative to the hope of breaking that degeneracy. You can also look at said active region as it approaches the limb, and you begin to get. But it's a challenge. I'll readily admit that.
Because I'm also interested during flares, so like it would be ideal if we could have gigahertz radio antenna in space at a different angle than we get.
Sure, yeah.
So sunrise is more megahertz. Is that correct?
The sunrise, the mission,
yeah,
is very low frequencies, low 15 megahertz or so down. So it's really not going to be a terribly sensitive mission, so it's only going to
So how do you quantify uncertainties in your predictions? And also, how do you determine the optimal training data size for your machine learning model?
Both excellent questions, and if we had more time, those would be the subjects that I would actually go into our discussion. So let me answer the second part. The idea of how do you choose the parameters, different aspects of the parameters, including the data size. So typically what you do in practice is that you have very large data sample, and this is, by the way, a very important practice that I should have actually mentioned, is that you don't just throw all of the data and train and then get a result. What you do is that you divide your data into fractions, where on some you do the training, and then you do essentially testing, and then you step through different parts of the data. That technique, which is used for almost every exercise using these things, is known as cross-validation. Cross-validation also, or a generalized cross-validation. it essentially ensures that you're not essentially just, it's not a cyclical aspect where you're training all of the data and then you're essentially getting same thing that was fed in, you're getting it back. It allows you to test for the diversity of what you're training on. And you learn essentially different aspects, the different parts of that distribution or different variations, renditions of that distribution. And then you test it on a different data, out of sample data. So that's a very important thing to do in practice. I should have mentioned that. And the first part of your question, can you repeat that?
How do you determine or how do you quantify uncertainties?
Oh, uncertainty quantification. So that's a very active area, by the way. There are lots of people who are doing that, and there are different approaches to doing that. The simplest way to do that is essentially using sampling strategies, statistical sampling strategies. So you have essentially these, remember, we talked about the probabilistic notions, and you can formulate these sampling strategies in terms of how you sample from your data and find empirical covariances based on your data, and then you can just track them through all of the steps in your problem. So that's I would say, the simplest and most prevalent approach to uncertainty quantification. But there are other emerging approaches to that as well. There's a lot of recent literature just in the last 5 years on that topic. If you're interested, I can show you.
So it's not a point that you mentioned in your lecture, but I wanted to ask, what is your position on the conundrum between stationary and moving type 4 radio bursts?
First, full disclosure, I hate the classification system used because the reality is far more complex. I'd rather see a physics-based classification rather than based on very primitive observations back in the day. For example, that radio CME I showed, well, that's really completely decoupled from what I see as the underlying physics of a CME ensemble of magnetic loops with synchrotron emitting MEV electrons entrained. They're also stationary type, thought to be trapped hard particles, you know, following a major eruptive event. So I have a position, it's hostility towards term type 4.
I guess this is a very naive question, but when you have the big F as a function of x, y, and w, if you can pull the w out, it seems more reasonable. Like I can look at the function of f and analyze it, right? But then if the w is inside the f and you have several layers of your neural networks, is it sensible at all to look at the functional form of big F and make any physical sense out of it, or do people not do that?
So we started with a case where W was outside, right? So it was a linear function of the weights. And the motivation for not wanting to do that was to essentially allow for nonlinearities that exist in our, essentially, the functional form, and so that we would have less restriction. So therefore, the ability to approximate more complex functions. That's the motivation for it. Now, the second part of what you asked was that, can we draw meaning from it? Can we interpret what that means? The whole idea of interpretability is, again, another very active area and is approached in many different ways. There's a line, if you just look at it, there's a lot of literature on how you would go about doing that. But probably the simplest way of talking about that, or at least approaching it, is in the way that you add additional constraints into the underlying governing processes into what generate those functions that you learn. I think the next speaker in the afternoon, who's going to talk about some applications, Enrico is going to talk about some applications in heliophysics. I think he will touch upon ideas from physics-informed machine learning and neural nets. And that's when you bring in some physically motivated constraints into doing the optimizations and therefore solving for the weights that are physically constrained and meaningful. I'm assuming that's the case. Is that the case? You're going to show some of those? Yes, there you go. Yeah. I didn't look at his slides.